So we're continuing our discussion of sequences. We call the nth term of a sequence, we would call that an, bn, or cn. You should think of an as a as a function of a sub n is a as a function of n, which is a function on an integer. So some terminology that has to do with sequence. The initial term of a sequence, at least in our class, is going to be the term a0, so it's going to be the 0th term. In general, when we refer to the current term in the sequence, we think of that as being an. The next term in the sequence, that would be an plus 1. And the earlier, or the prior term in the sequence, that would be an minus 1. Now, if I asked for the term that was two prior terms in the sequence, that would be an minus 2. But if I just asked for two prior terms in the sequence, then I might mean that I want both an minus 1, which is the immediate prior term, and an minus 2. So both of those terms. Now, a recurrence relation is a definition on a sequence of numbers that gives a formula for the current term in the sequence as a function of the prior terms of the sequence. Or it can give the definition for a future term in terms of terms that are further into the past. The order of the recurrence is the spread between the highest term in the sequence that occurs in the recurrence relation and the lowest term in the sequence that occurs in the recurrence relation. The order of a recurrence will tell us how many initial conditions we are going to have to correctly define the recurrence. So an example of a recurrence is an, the current term, is 2 times an minus 3. It's 2 times the term that's 3 prior terms back. Now notice this recurrent, this relationship between an and an minus 3 is the same as the relationship between an plus 1 and 2an minus 2. So what I would do is I would replace the n in this an with an n plus 1. So then this n also gets replaced with an n plus 1. And if I put in an n plus 1 here, that becomes an minus 2. Likewise, an plus 2, the relationship between an plus 2 is equal to 2an minus 1 is the same as this relationship and the same as this one. If I replace that n with an n plus 2, I would replace that n with an n plus 2, and if I take n plus 2 minus 3, I would get n minus 1. Likewise, another recurrence is bn plus 1 is bn plus 3. Notice there would be a future term, and then that's the current term. Cn is the 2 times Cn minus 1 plus 3 Cn minus 2, so we see two prior terms here. Dn is equal to 3 dn plus 1 plus 2 times 3 to the n. Now this might not look like a recurrence because the future term is here, but we would just solve this for dn plus 1, putting it in this form, so now we see a future term is in term of a term that's in the past compared to that one. So notice these three examples are not recurrences. I have an is 2 times n minus 1. There is no prior an or an minus 1 or other an term in here. Bn plus 1 is equal to n plus 3. There is no prior term here. And again, there is no prior term, and Cn is equal to pi to the n. So let's work with a few recurrences. The first recurrence we're going to take a look at is going to be this arithmetic sequence. And if we look at words to describe an arithmetic sequence, it is that the current term of a sequence is the sum of the prior term in the sequence and a constant amount which we will call p. So let's just go through the sentence step by step. The current term of a sequence, well, we would usually call that an, is always means equal. The sum, that means I'm going to add something, the sum of the prior term. Well, I know what the prior term is. The prior term is an minus 1, is the sum of the prior term in the sequence, and a constant amount, which we will call p, is the sum of the prior term plus p. So we get this recurrence, an is equal to an minus 1 plus p. So this would be our recurrence for that statement. Now we know the initial term of the sequence is x, so this is the initial condition. We get a0 is equal to x, and we would like to write down 4 to 5 terms in this sequence. So the first term I'm going to write down is a1. Well, using this recurrence, I know what a0 is, and if I substitute in here, if I substitute 1 in for n, I get a1 is equal to a0. Well, that's equal to x plus p. And now I can substitute in for a2. Now if I put 2 in for that n right here in my recurrence, I know that I'm going to get a1 plus p. Well, a1 is x plus p, so I'm going to get a1, which is x plus p, plus another p. Notice this is equal to x plus 2p. Now a3, that should be equal to, well, according to this, a2 plus p, so that's going to be x plus 2p plus another p, so that's going to be x plus 3p. And got one more, a4, well, that's going to be a3 plus p, so that's going to be x plus 3p plus p, so that's going to be x plus 4p. So now I've written all these terms down. There's a pretty clear pattern here. a0 is equal to x, a1 is equal to x plus p, a2 is equal to x plus 2p, a3 is equal to x plus 3p, a4 is equal to x plus 4p. I can solve this recurrence. I get an is equal to x plus n times p. So there is a pretty obvious pattern and solution right here. All right, so now let's work with another recurrence. So in this next recurrence, we've got the first term in a sequence is 0 and the next term is 1. Well, the first term in the sequence, the initial term of a sequence is a0. So we would set a0 is equal to 0. The next term is equal to 1. So we'd say, hey, a1 is equal to 1. Subsequent terms are defined as the sum of two prior terms. So if I'm looking for a recurrence formula for an, so the current term is defined as the sum of the two prior terms. So an is going to be equal to an minus 1 plus an minus 2. So that would give the recurrence relation. And notice that I also have the initial conditions right here. Now you know we often write this particular recurrence in another form. With a different letter other than a. But before we go into that, let's simply calculate 6 or 8 terms of the sequence and see whether or not we recognize what this sequence is. So let's just try that really quickly here. Well, I know a0 and a1, so the next term I don't know is a2. We know if I'm substituting an n is equal to 2 right there, then that has got to be a1, and that's got to be a0, so that's got to be a1 plus a0. So that would be equal to 1 plus 0. So we also find a2 is equal to 1. Then a3, that's going to be the sum of the two prior terms, so that's going to have to be a2 plus a1. Well, both of those are equal to 1. So that's got to be equal to 1 plus 1, which is 2. A4, that's got to be the sum of the two prior terms. Well, the immediate prior term is equal to 2, and the one that's further back is 1, so that's got to be 2 plus 1. That's got to be equal to 3. A5, that's got to be equal to 3 plus 2. I just summed the two prior terms, so that would be equal to 5. A6, now that would be the sum of the two prior terms, so that would be 5 plus 3, which is 8. Let's do a few more. A7 is going to be 8 plus 5, which is 13. And A8, that would be 13 plus 8. That's going to be equal to 21. So the next question I want you to think about is, do you recognize the sequence of numbers? It goes 0, 1, 1, 2, 3, 5, 8, 13, 21. And it may be that you did recognize this sequence. This is the famous Fibonacci sequence for the Fibonacci numbers. And may I note, we don't know how to solve this recurrence yet. We can look for a pattern here, but there is really no pattern that's apparent. And the alternate notation we often use for the Fibonacci sequence is we might call the terms f0 is equal to 0, f1 is equal to 1, and then we would define fn is equal to fn minus 1 plus fn minus 2. And right about the turn of the 12th century, so right around the years 1202, 1203, somewhere in there, I just want to tell you how Fibonacci came up with this sequence. He was asked to model a population of rabbits. Whoops, I cannot seem to write on here, of rabbits. So he started with one pair of rabbits. And he started with a male rabbit and a female rabbit, because if he didn't end up with a male rabbit and a female rabbit, he would only ever have one pair of rabbits, and that was not very interesting. And these were assumed to be babies. Well, babies can't reproduce immediately. It takes them a little bit of time to grow up. And it turns out it takes rabbit about a month to mature. So it would take the baby rabbits about 1 month to become old enough to get pregnant. So after 1 month, we would assume that there would again be one pair, male, female, of adult rabbits. And we would assume that those would be pregnant because rabbits would get pregnant immediately. That's how they work. Then at the beginning, it turns out that rabbits gestate for about a month. So at the beginning of the next month, they would give birth. Now we're going to assume that rabbits always give birth to another pair of male, female, and rabbits. So the next months we would have 2 pairs, male, female, of rabbits, 1 adult pair, 1 juvenile. Now, the adult pair would immediately get pregnant again, and the juvenile pair would have to grow up. So the adult pair immediately gets pregnant again. So at the beginning of the next month, they give birth to another pair of rabbits. So now we would have 3 pairs of rabbits. We would have 2 adult pairs and 1 juvenile. Well, our 2 adult pairs, the 2 pairs that were alive in the prior month, they would immediately get pregnant. And then we would have 1 juvenile pair of rabbits, and that pair would have to grow up before getting pregnant immediately. So the next month we would have 2 pairs of rabbits born, so we would end up with 5 pairs of rabbits. And of those 5 pairs of rabbits, 3 could get pregnant immediately, and there would be 2 more that would be 3 pairs would be able to get pregnant immediately, and we would have 2 more that were going to be juveniles. So that pretty much is where we're going and where we end up getting the Fibonacci sequence out of this. All right.